All right, Professor Garlick, let's get rocking and rolling because we got a long way to go and a short time to get there. We're going to be looking at some SAE Baja front suspension. I'm the suspension design lead this year, so I figured it would be a great place to start. We tracked the position of the shocks throughout some jumps and some drops that we did, and so I'll be looking at one of the drop tests. Here it is right in front of you. We recorded the position of each, or of the right shock there, and we went ahead and pulled that into Excel, and then I pulled that data from there over into Maple. That data I used a cubic regression, which you can see right here. I pulled the data in as vectors and went ahead and did a polynomial fit for a cubic to that. You can see the data here in this plot. That's the approximate position of the shocks from 0 to 270 milliseconds. Something important to note there. If I go ahead and move my way down, you can see this is the approximation we got. I came to that by using these initial conditions up here in the top left corner of the OneNote document. You can see that's my approximate mass, the velocity, the acceleration, and the position, all at time 0. We'll move down, and this is the free body diagram I used. We've got the mass times the acceleration in one direction, the other negative features in the other direction, as well as a driving force forcing the wheel up vertically. So that's going to be the mass that the shock actually has to control the motion of. I decided to use a transfer function as it lets me play with the different impulse functions for, say, different obstacles in the future without changing the actual entire function. I can just put it into the Maple worksheet and have it run the Maple worksheet to see how close we're going to be in the future. I moved down, I went ahead and used Laplace Transforms as it takes care of my initial conditions very early on. So if I can find a place in my data where I've got full extension of the shocks, say in midair or something like that, and it's not moving for any more than a couple of milliseconds, then I can start there and I can play with whatever I need to going on after that. I then wasn't sure what the impulse function would look like, so I tried a couple. I tried a constant function and a linear function. The quadratic function there I was going to use, of course, 32.2 coming from the acceleration due to gravity. The quadratic there you're not actually able to do an inverse Laplace transform of, so it didn't really work out. I used Wolfram Alpha for the calculations of the inverse Laplace transforms, and then I went ahead and did it again in Maple just to be sure that it wasn't there was nothing that I was screwing up or anything like that. This x2 of t down here, that's going to be of the inverse Laplace transform of my linear term, and then I went ahead and did a height correction just to make sure that it would match my data in Excel that we took and we did that cubic regression of. Nothing too fancy there, but then I did have to do some stretching, and I divided the x value in x2 of t by 144, and so then that gave me a function that so you could say that t is equal, or x is equal to t over 144, and that would give you the function that I went ahead and used. And that was just to take care of converting to milliseconds, as well as the difference between slugs and pound mass. So nothing too interesting there, but really useful thing to remember. So here's my final data, the regression plotted as well with the approximation. And you can see here that they're pretty close all the way through until you get to the very end. And that makes a bit of sense because we only have control over the damping for the rebound. So the shock is compressing all the way through here. We reach the deepest point in the travel, and then that rebound we don't have any is what we actually tune. So we could tune in some more rebound damping as we have in different directions. We have different damping coefficients with these high-end shocks. So it's a very cool feature, but it does make modeling this a little difficult because you need essentially two different damping coefficients. hopefully that gives you a bit of insight into how we plan to tune our suspension in the future and the methods that we're going to go about using them. A few of the difficulties are that the way I came about my forcing function was a bit of trial and error as well as an educated guess, being that gravity is the only thing affecting the body of the car. We don't truly either have critical damping. We're trying to achieve that, so that's something that is going to induce some error between the results and the model. We're also going to have a lot of friction in seals and bearings and bushings, slowing everything down. And then we'll also have a variable spring rate, as air springs are not actually linear. And since I'm not on campus, I can't go and weigh how much all of the arms and everything weigh, so I'm just approximating at that 20-pound value. Those are some of the sources for error, and I'll swing back over to those plots real quick just so you can see how close we were able to get for most of the bit, and then I'm going to try and get a little bit closer in the future. Hopefully that was pretty interesting for you. Thanks.